well, that's the first slide done. I was going to tell you who I was and where I work. So I work at Basho, as Bruce says, and we've been active in the Erlang community for maybe nearly 10 years, 8 years, that kind of time. I've worked at Basho for about 5 of those, and I've always wanted to come to this conference, the Erlang User Conference. In the past, Basho sent some very capable people, and they've done lots of talks, but they've all left now, so you've got me. I've been working on Riak for about 5 years, but we've recently rebranded it to Riak KV. So it's not really a Riak talk. There's some Riak in this talk, but I just wanted to make you aware of the rebrand. This is our distributed fault-tolerant key value database. So if you want to buy one of these, we've got a stand out there. You can buy one. Part of the rebrand is we have lots of databases now. We have this Riak TS database. So there's a demo out there in this. If you want to try that, you can race some scalemetrics and learn about time series. And I have to show this slide as well because part of what I'm going to talk about has been funded by the European Union, a research project called Sing Free. And there are other talks here today and yesterday from this project. Okay, so that's all the marketing stuff out of the way. Get on with the talk. It's kind of 4 short talks, so I'm going to have 4 sections of a talk. I'm going to do the what are CRDTs. So CRDTs, I've been working on them since about 2011, so we're all kind of mired in our own context, so I don't know how much other people know. So show of hands if you've heard of what a CRDT is. Wow, okay. You've made one or you've used them? Anyone? All right, okay. So that first bit, I'm just not gonna do the whole it's a joined semilattice blah 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 and show you hash diagrams. I'm gonna just explain the problem they solve. So where CRDTs fit into your toolkit, and then I'm gonna do a walkthrough in section 2 of the design of a general purpose CRDT set. So a set that everyone can use, and you'll see in lots of places now. Then I'm going to talk about how we shipped that back in 2014 as part of Riak, including some shortcomings we shipped. And then finally, at the end, I'll get onto the new work we're doing that addresses those shortcomings. So I'll get straight on with why CRDTs exist and why you've all heard of them. I'm not going to do the cap diagram. I'm not going to do the triangle with the CAP, pick 2, that kind of thing. I'm just going to say there are a bunch of different results that show there is a fundamental trade-off in multi-core and distributed computing between the desirable property of low latency and availability and the desirable property of strong consistency. You can't always have them all. I'm not going to tell you when you should pick which is right and which is wrong. I'm just going to say that there exists a trade-off, and some people have taken it for commercial reasons. The most famous being in 2007, Amazon presented this paper at SOSP, and it describes their scalable, eventually consistent, fault-tolerant key-value database, which we kind of based ours on. So Riak is a fairly faithful implementation of this. Dynamo exists to solve a commercial problem. So it uses lots of computer science research. It doesn't really do any new research. It just applies lots of existing theory to solve a commercial problem. I'm going to summarize that is you should always be able to add something to your cart. I mean, it's more complex than that, but essentially if you're shopping on Amazon, you should always be able to add something to your cart. That's what they want you to do. So Amazon's a multi-node distributed database that has multiple replicas of key values with many clients. But for this talk, I'm going to simplify that down. And I'm just going to use 2 replicas, 1 key, so one data item, because the key value stores, your keys and values are independent, so what matters for one matters for them all, and a single client. So that's all we're going to use to model some concurrency, show a problem, and then solve that problem with CRDTs. So Dynamo and Riak both have this very simple key value interface. You assign a primary key to something, so I'm going to use shopping carts for the first part of this talk. So you assign a primary key, Russell's cart. You call a get operation to fetch that data object. The application itself then mutates the object and stores it back in the database with the put operation. And and then the database nodes talk to each other with asynchronous replication to pass information around. And if you really want to always be able to add something to your cart, even if your database nodes can't talk to each other, you still want to be able to put things in. So if they can't communicate, if you've got a pair of replicas, you want to be able to write to them both independently and just deal with it later when you come to check out. Maybe read from all the nodes and find out what the current value is. So here's a sequence of operations with a single client operating in sequence, in temporal time. So there's no, you wouldn't think there's any concurrency here, but there is, because we allow our application to read in the past. It's always allowed to read and write, because we want to be always available to add things to our cart. So I'm shopping on Amazon. I go to some other store, because they're probably going to sue me at some point if I keep saying their name. And I search for headphones, I put them in my cart, and I store my cart on A. And then I continue searching, and for some reason, I don't download my cart from A, I download it from B, and B hasn't yet heard about my addition to A. That shouldn't stop us from shopping. Just because some message hasn't reached some node, I should still be allowed to shop. So I get an empty cart, I read in the past, I add something to that cart, and I store it. So this is the sort of diagram that's in the Dynamo paper to illustrate what just happened. You've got these logical clocks, which I'm not going to go into, that capture a relationship of happens before, and we've hit a point here where we've kind of diverged, or we've forked. We've got two copies of our cart on two different nodes. And this is great because we've got like low latency and high availability and opportunistic replication, and your business is really happy. And then you're an application developer, and it's your job to now write the checkout code where you read these carts. And what do you do? What do you do at this point? So in the paper, they've got two different advices for you. You can use timestamp-based reconciliation, which means every time you write the cart, you update some timestamp to say, when it was last updated. And when you come to checkout, you just pick the highest one. But that's not going to work for us in this case because we want to buy everything we put in our cart, not just whatever's in the last available cart. We do that reconciliation, we only get a hairdryer. So in the paper, they suggest you can use business logic or semantic reconciliation, which is like the semantics of the domain. So you think of a shopping cart. They say, well, you can imagine a shopping cart as a set. And so if you have multiple copies of a cart, it's like multiple sets. And how do you make one set from many sets? Well, you use set union. So if you do that, then we have the shopping cart we wanted, and we can check out and we buy everything, and Amazon's happy. And that's what happens here. You then hit this point, and that's called convergence. So we've seen divergence, and we've seen convergence, which is great, except you might change your mind about something and want to take it out of your cart. So let's go back to our diagram and walk through the same sequence. I read my converge cart from A, take the headphones out because I don't want them anymore, and then I decide I want to add something else, so I read my cart from B, so I read in the past. B hasn't seen the message from A yet, that hasn't seen the change. And I add something, and I store that. And then when we come to do a read, we've got a pair of divergent carts again, and if we run set union this time, we've bought the headphones after all, because union just takes the contents of both and smashes them together. So this isn't news to the developers at Amazon. They know about this. They mention it in the paper themselves. They say if you do this, then no add to cart operation is ever lost. So you always can buy what you want, but you might sometimes accidentally buy something you don't want because deleted items can resurface. So that's the problem we're looking at. That's like an encapsulation of the problem, one example of the kind of problem, which is how do you write code to converge those divergent replicas in a way that's correct. Apparently it's really hard. So Google have lots of really great engineers. And they decided it was such a hard problem, they would write a system that didn't allow this. They have a global spanning CP system that doesn't allow you to have these divergent replicas because it's too hard and not worth the performance gains. So that's the kind of challenge that we're looking at as software engineers. Another example of how hard it is from one of our customers who said that moving from SQL to NoSQL, specifically to Riak, one of their biggest challenges was going to be writing code to handle this converging divergent replicas. So that problem is where CRDTs come in. So CRDTs are data types that converge automatically. So rather than having to do semantic or business reconciliation logic, the data types already have that. They're abstractions that will converge automatically for you. So you can think of them as off-the-shelf merge functions. And they are literally data types. So like I say, it's not business logic. It's abstractions you're used to using, like maps, sets, integers, booleans, those kind of data types that you're comfortable with as an application developer. But they converge automatically. And everyone probably knows the name by now and the joke about the name, how it's convergent or commutative or conflict-free, but the C stands for many things, but they're replicated data types. So hopefully that's enough to motivate why they need to exist, because you want to have these high available systems, but you don't want to pay the cost of writing code to merge divergent replicas. And I'm going to then, excuse me, look at how we can make a CRDT set that we could have used for that shopping cart that doesn't have that problem of the reappearing delete. So actually, I'm not going to use shopping carts in this section. I'm going to pretend that my friend list or friend lists on social networks are sets instead for a bit. So sets are interesting because we can because they're fairly fundamental, and we can get a long way in a short time explaining how they work. But they're also valuable. So the same customer who had trouble with the merge function says that they can model a fair number of their use cases in sets alone. So they can save money, engineering time, just by using off-the-shelf CRDTs. So let's look through the design of a set. So that paper I showed you a second ago, that lists a bunch of different set implementations. They're not all valuable. Only really one of them is generally useful, but we can think of them as steps on the way to the generally useful set. So the first one is something called a grow-only set. Here's my divergent replicas again. And if we're only allowed to add things to the set, then set union is fine. We can use that to turn this pair of sets deterministically into a single set. And that's simple, but we can't take anything out. So we can't use this for our shopping cart, or we can't use it for a social network where we might fall out with people. So the next set in the paper is called a two-phase set. And it's made of a pair of those grow-only sets. So you can add friends and put them in the add side of the set, and you can take them out and put them in the remove side. So it's like tombstones. But that's all you can do. So if we look at this structure, we see that the only friend I have, the logical friend in my set of friends, is the friend who hasn't been removed. So if you're in the add side but not the remove side, then you're in the set. And this is kind of cool because the value is different to the structure. So most CRDTs are like this. They have a different structure to the actual logical value. So we can take things out now. But we can't really use this on our shopping cart yet because you can't change your mind. If I re-add Shelley, I decide that actually I do like her, then it doesn't make any difference in this set because there's a tombstone there saying she's not in the set, and we take the disjoint of these two sets to decide who's in the set. So we want a generally useful set. This isn't it yet. I'm going to look at something else in the paper called a unique identifier set. Now, I have no idea of a use case for this. I bought too much beer at System Bolliget. So if you can come up with a use case, a genuine use case for a unique identifier set by the end of the talk, tell me. I'll give you a beer, because I can't think of one. But we do use it in a second to make a generally useful set, as a compositional element. So here's a pair of unique identifier sets. They look just like G sets, except we've got, I've used integers here, but these have to be globally unique tags. So in most of the implementations I've seen, the naive early CRDT implementations, these were something like UUIDs, great big long strings. And so when we union these together, we can see that this friend Shelley has been added twice to the set of friends because it's got two unique tags. So I'm not sure what value that is on its own, but we can use it to compose something called the observe remove set, or what these, I think in most literature I've seen recently, is called the add win set. So that looks like this, a pair of those unique identifier sets. And I'll just walk through how this works. And this is our first generally useful, general purpose. You can use it for anywhere you need to use a set, CRDT set. So I've got on one replica, I've added my friends, and I've removed them all because I don't like them anymore. And on the other replica, I've added a new friend, and I've changed my mind about Shelley. I've re-added her. So when I merge these two together, I get this structure. And the membership of the set is any element that has a tag in the add set that doesn't have a tag in the remove set. So in this case, Shelley has been removed at tag 1, but not at tag 5. So she's still in the set. And this trick is called observe remove. That's why the set's called an OR set. And it means that replica A is only allowed to remove the tags that it's got a copy of, that it's seen or observed. That's where the name comes from. And it gives us a semantic of add wins. So we see that we've concurrently added and removed this one friend, but the add has won over the remove. And this is our this is our generally useful set that you can, if you want to model anything that you can, if you can pretend that shopping carts are sets, you can use this. If you pretend that friend lists are sets, you can use this. But I mean, is it good enough to ship in a product? And it's not really, because you have to keep information forever. You have to keep these tags around forever, the tombstones, unless you have some kind of synchronization method to get rid of them. And so if you add 1,000 friends and remove them all, the empty set logically takes as much space as the set with 1,000 friends in. So although this is like the behavior is good, we like how it behaves, we probably can't, as engineers, ship a product with this inside it and then say to people, I'm sorry, your disk is full. But then the same academics who came up with all those designs then came up with an optimized version a year later in 2012. And we gave this the catchy name Observe Remove Set Without Tombstones, or SWAT. Although I think more recently in the literature I've seen it referred to as the optimized AdWin set, which is it's a much better name. And considering this exists and the unoptimized one isn't necessary anymore, we should just call this the AdWin set going forward. So I'm going to show you how this works. And when you've seen how this works, you know as much as all the people who are implementing CRDTs know. So we need to know a little bit about version vectors, but we're not going to do a whole kind of version vectors tutorial. I'm just going to tell you how version vectors help for this structure. So remember we had a pair of replicas. We're going to call them A and B. And in our version vector, these replicas have to be like globally unique names. So we have A and B are their unique names forever. And as far as the structure goes, a version vector is just a list of two tuples. The first element is the identifier of that replica, A and B. And the second is how many times it's added something to the set. So A's added 2 things, B's added 1 thing. So it's a really compact summary of all the action of those 2 actors. And if we have, if our actors are globally unique, and if they generate a sequence of increasing integers, we can use that pair as a tag, as the unique tag for these, in the unique element set. We have to tag everything uniquely. These are very compact, unique tags. And we're able to summarize them in the version vector. So we have a very compact summary. So let's see how this works. Replica A, add a friend. And now I have a version vector at the top here as well, summarizing all the events that A has done. I send that to replicate it over to replica B, and its version vector summarizes everything it's seen now. It's seen this tag A1. Add some friends on B. They all get tagged, and we have a summary in the version vector saying B has done 3 actions. Send those over to A, and its version vector reflects what it's seen. So far, nothing exciting, but let's get some divergence. So let's remove Phil altogether and add a new friend on each side, Anna and John. And the thing now is that with this structure, we can just drop the data. We don't have to keep that tag around or that information around. We just remove it. And when it comes to merging, we just look at the tags. So tag A1 is in both. We're going to keep that. B1's in both, we're going to keep it. B2's only on one side. So how do we decide if we keep it or throw it away? We look at the tag, and we compare it to the version vector. So this version vector, B3, has definitely seen tag B2. So we know that we mean to remove Phil. So we just drop him. B3 is the same, it's on both sides. Then we get to tag A2, it's only on A. Is it on A because B removed it? Or because B hasn't seen it? And we do the same trick. We use the version vector. We see that A1 is less than A2. And B's never seen this value, so it should be in the set. And the same with John. And so we end up with a set that size-wise is about the same size as the number of things that are in the set. And we have this nice compact version vector that represents all the tags we've seen over time. So this is the general purpose CRDT set that you'll see in, what's your product called? Yeah, so I think they use it over at Mesos. I know that Phoenix has this for its presence, for sharing presence information. Riak ships it. There's a bunch of products that use this. This is the general purpose one that people are using now. It's got this semantic of AdWins via this trick of observe remove. And hopefully after seeing that, you should be able to write your own quite easily because it's a fairly simple implementation. So with Riak, we have customers who have that divergent replicas problem. And we've seen that the academics have come up with this nice solution to it. So we decided that we could ship this as a solution for our customers. So we could just say, here's a paper, you read this paper and you can write CRDTs and you haven't got a problem with divergent replicas anymore. Or we could do what I think most people probably do, and we thought we'll write a library. We'll take these data types as defined in this paper, and we'll implement them. I'm only going to talk about this one. I'm just going to talk about the set only. So we've got this module, Riak DT or SWAT. I wish we'd gone with adwin set, with a version vector and some entries and all that. So we take the paper away from the customers and say, here's a library. We've solved your problem for you. You've got divergent replicas. Just use this. But I don't think that's good enough, because if we have these idea of version, if we have version vectors and actors, so this is the data bus. This is something that one of our colleagues, Angel Sanchez, made. I'm going to switch to this from now onwards, because it's nicer. If we have many, many clients, we have very, very big version vectors, right? So we might end up with metadata greater than our data. So that's not a great idea. So maybe giving the library to the clients isn't very good. But worse than that is if we give the clients just a library, we take something away. So here I am, wanting to add friends to my friend list. It's currently empty, and I download it. As a client, I pull the friend list back, and I generate a unique tag, the first tag for this set, client 1, tag 1, and I add a friend. But then I read in the past on B, so I get the empty set, and I generate a unique tag for my friend Bob. Now you see what's wrong here, right? These aren't unique tags anymore because I've read in the past. Because I'm trusting the database to remember for me, I have to be able to read my own rights from the database. So I've put a consistency constraint or requirement on the client if I give them a CRDT library and say, here, you just use a library and you'll be fine. Well, you won't be fine. You'll have to be able to read your own rights, and that's a cost. So take the library away. You can't have that. We're going to put the library inside our database instead. So we're going to, we're not going to say you have to use Riak DT. We'll say we'll put Riak DT inside Riak, and we've already got replicas, and they're called vnodes, and they're the actors in the system, so we'll use those. So now we have to just answer the question of how you use this library if it's inside Riak. So if you remember for Dynamo and Riak early on, I said the API is really simple. You do a get to get the value. The application mutates it, and then does a put to store it. And that's probably okay for something like a shopping cart, because they're kind of small and maybe short-lived. But what about your friends on a social network? Or my friends, that's quite a small list, but the Zuck list, Zuck's got 78 million. It keeps changing, actually. When I first started this talk, it was 76 million. He's got 78 million friends now, probably more already. It doesn't make a lot of sense to do get Zuck's friends, bring it down to the application, add a new friend to it, and then send it back to the server. That's a very expensive operation. So we thought maybe we should give an operational API instead. So the clients can just tell the database, add this friend, add that friend. And the database server can take care of inserting them into the sets and replicating. So that kind of works for adds, but it doesn't really work for removes because of this trick we have for deciding what's safe to remove. If you can only remove what you've observed, then you've got to do some kind of read to observe something in order to then say, remove these tags, right? So we're kind of forcing you to read if you want to remove. So that's what we shipped in 2014. We have customers with this problem. We took the academic paper, we made a library of it, and we wrapped it with a basic operations API with this additional context for removes. We've got vnodes, or the Riak replica nodes as the actors, so the clients act at a distance, and we have full-state replication. So we have a set. Riak is a key value store. We already have something we store in Riak. It's called a Riak object. It has a version vector for detecting divergence. So we just stuck our set inside the Riak object. And then we take our Riak object and we stick it inside a key value store. And this is kind of key to what I'm talking about. So each key maps to a set. So if you've got Zuck's friends, you've got a key Zuck's friends, and you've got a set, an object on disk. My shopping cart, you've got a set on disk, and so on. So as a visual mnemonic for this design, it's kind of like this. We've got a set inside an object inside a key value store. So let's see how that behaves. You tell Riak, I want to add a friend to Zuck's list. So the data bus node, it like coughs up Zuck's friends from its storage organ there, and it pulls out the version vector, it increments it to tag, tag that new element, put it back in the set, serialize it, swallow it back down again, send it across the network to the replicas, who will cough up their copy, run that merge function to get a single set, and store it on disk. Problem? Just a bit. This one key to one set mapping means we've got poor write speed, and hopefully following through you can see obviously where that comes from. That in order to change the set, we have to read and write the whole set, and that's expensive. So rather than having an intuition about it, here's a graph. X is cardinality, Y is time. So the bigger the set is, the longer it takes to add an element, and that's not really intuitive. If you've used a set before, that's not how they behave typically, so it's not really good enough. Here's a benchmark. You don't have to be able to read the figures really, but what matters is that as the set grows, that green line goes down and the red lines go up. And that's not really the kind of performance our customers like. And there's another problem. There is large object databases exist for a reason. There's a difference between a large object store and a general database. And Riak is a general database, and it has a kind of limit on the size of a single object, and that tends to be a megabyte. And it's going to be hard to fit 78 million Zuckerberg friends in a single meg. So I'm going to try and catch us up now. We've seen a problem. We've seen an academic solution to the problem, and we've seen an attempt to solve that by shipping a library with an API in a database. And now we've seen the problem with that. And we know that what we shipped is reasonably valuable because we've got people using it, and people are using it and telling us this is what's wrong. So we know what's wrong because it's valuable, it's just not valuable enough. And this gives us a very, very clear sort of mandate on what to work on next, or what we're working on now. People are happy with the behavior, they like the high availability, but they just want to be able to, they don't want to pay the latency cost of that every time I change a set, read it and write it. And they want to store more information in sets. So it's a really clear design brief. And so this is like the kind of work, we've got not much time left, but we don't really need it because it's a really simple thing we've done in order to give us, to solve these aims. So the name Big Set is terrible. I think it was originally kind of a joke, but at the moment it's stuck. I'm hoping we have product people to give it a better name when we come to releasing it. And this is the whole trick of the design, is that rather than thinking in terms of abstraction, a library that you expose over an API, we've kind of taken what we've learned about CRDTs and built them into the database, thinking about the things that matter most in a database. And that's I/O. We don't want to burn IOPS on stuff we don't need to, so we want to keep the I/O down. So we're using a key value store called LevelDB. It's a sorted string table, key value store. We're going to use the sorted nature of it later. But we have expertise at Basho in this product, so that's one of the main reasons we use it. And what we've done, essentially, is take that module, that Riak DT or SWAT, and break it out. So whereas before we had a key that mapped to a key which described a set that mapped to the set, now everything that's in this set structure gets its own key in level. So there's a version vector that gets a key. Each tag for these tagged elements, they all get a key. So it sounds like a bit of a trade-off of space for time. So we're going to take up more space, but LevelDB has great compression, and it also factors out common prefixes. So we don't even pay a great deal more for space. And if you'd all gasp now, no? OK. So this is what happens when you run that same workload on Big Set. X is cardinality again, and Y is time. And although it's a lot faster, what really matters is the trend, is that we're seeing that even when the sets grow large, it doesn't cost any more now to add and remove an element from the set. So that benchmark, we ran it again, and this is the behavior we get. We get that flat line now. So the latency stays constant, and the throughput stays constant, even as the sets grow. And you see them side by side. So how does that small change, reap those benefits? If we walk through our our use case again, let's add a friend to Zuck's friend list. So we tell Riak, add Shelley to my friend list. Now all we have to cough up from the storage node there is the version vector, and that's it. Regardless of the size of the set, we just need the version vector. We increment it to get a new tag. We add that new tag to the new element. And because LevelDB allows us to atomically store multiple keys, we store those two together atomically. And because of the sorted nature of LevelDB, that new friend will find its way to the right place in the set on disk. And then we take advantage of some more academic work. As I mentioned earlier, we used full-state replication before, but the same academic team came up with the idea of delta replication, where you just replicate the changes in the CRDT, and we do that for big set. So we just send over the difference, this new tag, this new element. And at the replica, same thing. Gone the wrong way. All you have to do is barf up that version vector. If you've already seen this tag, if the version vector says you've seen it, you're done. There's no more work. If you haven't seen it, then you add the information and you store it down, and that's it. So that's all we've had to do to get that massive performance improvement. So pretty easy, really, and pretty nice. So when I first, we've got all these complexities now. So that's not really it, obviously, because there's time left, and I didn't go that fast. So I'm not going to talk about each of these because there isn't time for all of them. But these are all complexities that have come up from this design. Reads are more complex. The version vector is more complex. We have these processes inside Riak that are much more complex. And it's all come from breaking that mapping up from before one key to one object. Now we represent an object across many keys. So before, these operations occurred on a single key, which made them simple, and now they have to go over the set of keys, which makes them complex. And I'm going to look at only one part of this. I'm going to look at reads, because I'm sure there must be someone in this room who, as I was explaining that design, would have gone, well, your reads are going to suck now. Because that's what my colleague said when I first told them the design. They said, your reads are going to suck. And they were right. So this is a graph showing the green line is reading 100K element set off Riak, and the red is off big set, and there's a delta. It was a lot slower. It was so slow, we could only get 4 sets a second off, 5 sets a second off disk, so 500,000 keys a second off disk. So I'm going to look at why and look what we did to fix it. So this is kind of logically what a big set looks like on disk. We've got a version vector at the top. You've got a set of elements, ordered. And when we want to read it, what we do is we read that version vector, and then we iterate over each of those elements, and we transform it into that adwin set that you're so familiar with now from earlier on in this talk. And it's just classic death by 1,000 cuts, right? Where C++ is a level DB, it iterates, seeks to a key, reads it, hands it to Erlang. Erlang, fold accumulates it, runs some logic, says thank you, can I have another? And Level go, here, have a key. And so we go over and over again, over 100,000 elements, or Zuck's 78 million friends, and that takes a long time. So in retrospect, the obvious answer, an engineer from Basho called Angel Sanchez did this work, is we just buffer up. We fold over a large chunk of keys. We iterate over a chunk of keys into a buffer and hand those over to Erlang. And we continue then iterating in C++, and so we've got the next chunk ready for Erlang when it's processed those keys, and just do it that way instead. And that saved us a huge amount of time. That gave us a huge performance increase. The next major change that we had to make was just to stop encoding and decoding our keys. So we need the keys to be sorted. We want all the keys for the same set to be together. We need the version vector for the set to be the first thing for the set, and then we go through all the elements in order. And we were using, these are Erlang terms, and we were storing them externally sorted, so we used the library for that. And again, it's death by 1,000 cuts. When you're deserializing millions of keys, then every time you have to deserialize, it costs you time. So we just we were lucky enough to have some level DB expertise on staff, and they said, you don't need to encode, just use null terminated strings as fields, and it will sort correctly. And it did, and got us another huge performance increase. So reading a big set, I'm going to just skip through these quite quickly. You have a client asking to read the set. An FSM starts up, contacts a bunch of replicas, in this example 2, and they all stream these blocks of keys off disk. And because they're ordered, we can take block one from both replicas, and they represent an equivalent subset of the CRDT. And so we can do a merge. That merge we looked at earlier on, we can perform that on a subset. So we can incrementally merge a very large set. We don't have to read the whole set into memory. We can just read the first 100,000 elements, merge those, send them down to the client who can start processing or pagination, and so we go. And that got us read performance that was very, very close to current React. So there's still a slight penalty. You still have to pay a little bit more to do reads this way. But why are we reading the whole set? If we really have got this massive set, why aren't we just querying it? And the answer is because you have to, right? With React, you have to. There's no choice. If you want to ask the set anything, you've got to read the whole set. So this design means that you can have queries. You can have subset queries, range queries, pagination, that kind of thing. But I'm going to look at one query that's important, and it's a membership query. So if you remember back, this trick we have for correctness, this observe-remove trick, you have to see something in order to be able to remove it. And that, in React, forces you to read the whole set, because you want to remove one element. And if you're talking about the Dux friend list, that's really wasteful. So with this design, you can read a single element. You can read a single member from the set, which gives us a cheap membership check. So it makes it very easy for the client to be correct and always observe before removing. So how does that work? Well, if you're a client, you say to the system, is Bob a member of the set? And the FSM sends out to the replicas the question, read Bob. And we read the version vector from disk, and then we just seek to the keys the tags for Bob. And because we're ordered, and they'll be co-located, it's just to seek and iterate till we've got them all. And we turn that in memory into that optimized AddWin set that you now know how works. We have a pair of those, which we can send down to the FSM, who can merge them. And because the version vector covers everything, and we know that we're looking at a subset only of these elements, we can do that merge correctly on these subsets. And so we can answer the client, yes, Bob's in the set, but with only these tags, and we can do it by only reading a very small amount, the minimum amount of information rather than the whole set. I mean, that's way more efficient than reading, it says 77 million here, but he's probably got 79 by now. Million friends just to remove one. So I'm going to stop there with the big set stuff, and that's just an intuition of all of the kind of work we've been doing and how it solves a scalability problem. I'm just going to quickly talk about what we're doing next. I don't know if any of you went to the time series presentation yesterday, but my colleague Gordon mentioned that he has a prototype of doing SQL over maps and sets of CRDTs. So our plan is to use this design technique we use for sets to do maps of maps and maps of sets, and model tables, basically, eventually consistent tables inside React. So that's not, first we have to make the maps, and then we have to figure out if we can do the joins and stuff. But it's what the direction we're going in is. I think about there time-wise, right? So just to sum up, CRDTs make eventual consistency easier on developers. That's why they exist. They solve one problem and one problem only, the divergent replica problem. You've seen there exists an optimized AddWin set. Hopefully you could make your own now if you wanted, because it's really quite simple if you walk through the steps. But to solve a problem for customers, it takes more than a light. It takes more than a paper, and it takes more than a library. You have to really think about how the properties fit in the system you're making. So CRDTs in a database are very different from CRDTs for points of presence and different kind of products. And a little engineering goes a long way and gives you an awful lot of opportunities. So if you want to read more, we have a paper upon archive that we presented at PAPOC that gives you into more detail about how Big Set works. And we're hiring, and please visit the stand. And I'm done, so thank you. Oh, questions?
Oh, I have to use the mic. For deleting sets or the big hypersets, is that just a single operation, or how would deletes work?
Delete a whole set?
A whole big set.
Yeah, the entire set. Okay, so We haven't done that yet, but it's very, very simple. Because what I didn't cover in this talk is this idea we can use LevelDB's compaction to remove elements from the set. So LevelDB has a process that runs through the set and compacts or grooms out deleted keys. It's an append-only store. It doesn't ever remove anything until compaction, when it writes down to lower levels. So in order to delete a set, you take the version vector for the set, and you copy it into another key called tombstone. And that says that every tag in that set is to be removed. So that's logical deletion. And then compaction runs and physically deletes all the keys.
Okay.
So that's how we delete the whole set. So it's unlike with React, we have to read the object and delete it. You just say delete it, and we copy that version vector. So a concurrent add of an element won't get deleted because it won't be covered by that vector. Anyone with a use case for a unique identifier set? Oh, I'll drink the beer then.
Right, round of applause for Russell Brown's CRDT with React.
Thank you.